Hey everybody, today we're gonna continue our journey on the intro to reversing track on HackTheBox. This is You Can't See Me and let's just jump into it. Checking out the challenge. So we have to start somewhere, and I always like to start with a little bit of initial enumeration just to see exactly what we're working with. Now HackTheBox gives us a zip file which we can obviously easily unzip, and that yields us with the auth file. But what is this file? Well, using the file command we can shed some light onto that, because that will show us information about what kind of file we're working with, and if we run it we see here that it's an ELF 64-bit executable. ELF stands for executable and linkable format, and it's kind of a standard that is widely accepted on Unix systems for binaries. So yeah, this can probably run on Unix systems. I'm using Kali here, which is running on Unix, so that's perfectly fine there. Lastly, I also want to point out that we see here that this binary has been stripped. Now, this is a technique that's done to decrease the file size of such a binary, and it's simply put, it just removes all of the simple symbols from a binary. Now, symbols are things like function names, variable names, and all that kind of stuff. These are removed, which obviously makes the binary smaller, because your computer and the assembly code, they don't need things like variable names and function names. However, it makes reversing quite a bit tougher, but that's all good. We can still work around that and figure out how this works. But okay, I digest. Now we know that we can run this binary on a Unix system, so let's just run it. Let's just see what's happening here. So I run /auth and it welcomes us. So yeah, let's just respond with welcome back. And now it replies that we cannot see it. Kind of strange, but yeah, it wouldn't be as easy as just running it, I guess. So let's find out more ways of getting some information out of it, and one last very simple way is through running strings. Now, string is a command that will show us all the bytes in the binary which can be shown as ASCII and that have other ASCII characters around them, which in human terms just means that it's showing all the text found in the binary. And if we scroll a bit in all of that output, we can find some of the things that is already set to us, such as welcome, but we also see presumably a flag format and a weird string saying this is the password. But okay, that didn't give us much more information, but overall we've just gathered a bunch of information, and now we can actually get to reversing this program to see what is happening on the inside here. Reversing with ltrace. Let's get into how we are going to understand what this binary is doing, and for that we are going to be using ltrace. Now, ltrace is a great utility that is going to trace library calls in your binary. Now, what trace library calls, what does that mean? Well, a library is can kind of be compared to a module in Python. In Python you import something, and then you can use the things where the code has already been written. You don't need to write code for that. In the same way here, a binary can use a library, and a library such as libc can do things like printing out to the screen with printf, doing a string compare with string compare, doing a gets, so getting input from the user using fgets. Those are all kind of things that you don't want to write code for, so a library can handle that. And ltrace is just going to show you all the library calls that your binary makes whilst running, and this can give you a great idea of what is going on in the background while your binary is running. But in order to make that make more sense in your head, let's just run this. So I'm going to run ltrace on our auth binary, and we see that we start out with a printf of welcome, and obviously that's what happens. Welcome gets printed out. Cool. Then we're doing a memory allocation. We don't need to be worried with that. But after that, we're doing an fgets here. And this is getting input from the user. So here we can type our input. And I'm going to press enter. And now we see a lot of stuff appeared here. Because what happened after we entered our input? Well, then a string compare happened. And a string compare compares two strings. it compared the string whoops, you did see me with our input. And the result of that is 8, which in string compare has to be 0 to be true. So the strings were not the same, so it printed out, I said you can't see me. However, now the program has kind of spoiled to us what it's comparing with. So we can just copy this string, and let's see what happens if we do pass this string compare, if that's the same. So I'm gonna run ltrace again, and this time I'm just gonna enter the string that we just saw. In this case, we can see our string compare, the result is 0, so that's good, that means true. So we print out, well, HackTheBox, whoops, you did see me, which is the flag. And let's just quickly run that without ltrace. There you go, you can see that it prints out the flag, which is that secret string wrapped in your flag format. And yeah, that is how you can solve this challenge really easily with ltrace, where you can just trace what the program is doing, a really useful utility. However, do not leave yet, because you may be wondering why our strings command didn't show this string, because obviously this is a string, it has to be contained in the binary somewhere. Why did strings not show it? Was strings just not working? Did we not look close enough? Well, that's what we'll be covering in the next section. Reversing with ghidra. Now this section can get a little bit crazy, however try to follow along as I explain this. So I've opened this binary up in the amazing tool ghidra. Ghidra is really great because it can show us some pseudo decompiled C code that we can work with way easier than assembly code, so I highly suggest getting acquainted with this tool. But I've just opened it up, and in the function list here on the left we can see a ton of these functions. However, they don't have names, they're just called fun, which is not that fun, it stands for function. But yeah, we don't know where to start. However, there's always going to be an entry function, and that entry function contains this __libc_start_main, which points to this function as being the main function. So just for the sake of this video, I am going to rename this to main. So now we've created our own main function, and now we can go to there and see this. This is our main function. And we immediately can see some elements here. We can see welcome, so we know that that's right. But let's just quickly go through this to make more sense out of it. So first of all, these declarations in the beginning here, they are just to create space on the stack. So they're just reserving that space on the stack, so the stack is being built here. Then we have this whole section here where we are initializing a lot of these values to things, and we see in local 28, for example, here contains this _is backwards. Look for this character array here, where ghidra already shows us the characters for REs, but it shows this is backwards, okay? Then we have local 20 showing us the pass backwards, and then this last one will probably show word or draw backwards. So yeah, that's what these three variables will contain. Then these variables here at the bottom, they look very similar, but they just contain random values seemingly. Like I see a U double quotes, comma, 17H, comma, things that aren't easy to make sense out of. And the same goes for these two others. Then we get to this kind of difficult for loop that we'll get into deeply in a bit. But skipping that for now, we move on to an fgets, and this is where we're gonna get the input and store it into local 30. So I can actually also rename that to be input. And then we're gonna do our string compare with our input and this other variable that we don't know. And this is then the result of that string compare. So I can also rename this to string compare result. And if that is 0, then we're gonna print out the flag. If not, it's gonna say I said you can't come in, and that's or you can't see me. And that's really quickly just what this code looks like. Obviously the decompiled C code here, but there is this big part that we haven't covered, and that is this for loop. So let's just get into that. So this for loop starts with this local 10 equals 0, local 10 smaller than 0x14, and so on. And it's clear from that that this local 10 is an I. So okay, so for I equals 0, we're going to go until how many times? Well, 20 times, because 0x14 is 20, and then we're going to increment by 1. Now, what are we going to do? Because this statement looks very, very difficult to understand here. However, we have to break it down in small parts. The first part is here, the pointer to local 28. Now, local 28 is on the stack, and we're going to get a pointer to that position. Then we're going to add I to it. Okay, I is our counter, so this is going to loop over local 28, adding something to it. What does that mean on the stack? Well, that's why I've quickly drawn a stack that you can see here, and this is just a theoretical view of a stack. It doesn't have to be exactly correct, but we see that local 28 is on there. Below local 28 we have local 20 and local 18, and then obviously all the rest. Now, in the beginning we select the pointer to local 28. That's here. Then we're going to add I to it. In the beginning I is 0, so we're going to add nothing to it, so we have the first byte of local 28. Then I is going to increase. I is going to be 1, so we take the second byte of local 28. Then I will be 2, 3, 4, 5, 6, and 7. So we take all of the bytes from local 28. And then eventually I will be 8. And at that point, local 28 is only 8 bytes long. So at that point, we're jumping out of local 28 and into local 20, the next on the stack here. So then we're taking the first character of local 20. And then we do that for 8 times, and then we take the first character of local 18 and so on. And that's how we pretty much select all of the characters in these variables here that you can see. So the first time it will be the T, then the H, then the I, then the S, forming this. But we're obviously selecting that, and then we're turning it back into a character, so taking the character, but we are doing an assignment here. So we're actually changing this. So we're going to loop over all of these characters and we're going to change them. And obviously we need to know what we're going to change them by, because that will be the solution. What are we going to change them by? Well, we see the same construct here where we have a local 48, so another string, and we're adding I to that again, which will again do it 20 times. So that's selecting that byte of local 48, local 40, and then local 38 and converting it back into a character. So in the first time it's going to be an M, then it's going to be a little cap, then 2 ampersands, then an F, then an I, and so on. Okay. However, then we're adding a \n, so we're adding a new line to that. What does that mean? Because now we have a character, and we're adding another character to it. However, we're placing 2 characters into a single character. So how does that assignment work? Well, this is not like Python, where 2 characters added together form a string. No, in this case, we're just adding the hex values together, and the result of that is then your output. So let's just quickly do that for the first one here. So the first one is going to be the first character of local 48, which is going to be M. Quick note, this is all backwards because this binary uses the least significant bit. That means that the least significant bit is the first one, which means that everything is backwards. This is something that you saw in the beginning when we ran the file command. However, more on this will come in the later videos in this series. But for now, just remember things will be a bit backwards. And that's annoying, but that's the way it is. So okay, the first character we grab is an M. Then we're adding a \n to it. Now \n has the decimal value of 10, as we can see here. So we have to add 10 to M. So okay, M. Then we have N, O, P, Q, R, S, T, U, V, W. W will be the first character of the output. Now, we can actually check that with our actual flag. Our actual flag was whoops, starting with a W. So that is correct, which is really cool. And that holds true for all of these characters because we'll add 10 to all of these characters in these variables here. And that is how you can kind of look through what makes up this resulting string. And this also explains why our resulting string cannot be found when we run the strings command, because it doesn't exist when the binary isn't ran. It only starts to exist when it's created by this for loop. And that is why it was not visible when we ran the strings command. Conclusion and outro. Today we solved the second challenge in the introduction to reversing track by HackTheBox. We solved You Can't See Me. First of all, we did some basic enumeration and we saw that we couldn't find a password using strings. Then we tried to use ltrace to trace the library calls in the binary, and that way we uncovered a secret. We uncovered the secret string that we needed to get the flag. Then we pondered, hey, why was that string not included in the strings command? So we used ghidra to dig deeper, look into the bits and the bytes, and to check what that mysterious for loop did and how this actual password was generated within the binary. And that's all we learned today. I hope you enjoyed it and I hope you learned something new today. If you did, let me know down below in the comments. If you have a friend who's currently learning reversing, then please send this video over to them. It helps me a ton if you guys share my videos. But yeah, that's all that I had to say today. I hope you enjoyed it and I hope to see you back in the next one.